All right. This is Harvey, the harvesting robot. This is our project for embedded systems. My name is Brandon Ellis. I'm with Juan Chen and Luis Cardenas, and we will be presenting what we've been working on. All right, so just to go over, we're going to talk about the premise of our design and then the software and hardware. And then we have a video demonstrating the project as well as some of the struggles and what we've overcome. All right, so the premise of this project is obviously it's a harvesting robot, but we wanted to think about the applications of it a little bit more. And something that came to mind when we were conceptualizing it is greenhouses. So greenhouses are becoming very popular in many parts of the world, especially in colder climates, because they are very productive, but they are buildings. They're essentially growing stuff inside, and so traditional harvesting machines like your combine harvesters and other such machines aren't really possible to have in a greenhouse. And so as a result, a lot of the work done in greenhouses are a lot of it's done manually, and so we kind of wanted to explore the concept of a robot designed for use in a greenhouse. And so that's what we are going into this. That's what we were decided to go into this for the project. So we wanted a robot that can harvest some more complicated labor and some more complicated crops or rather some simpler crops that would be more desirable to mechanize. So we chose potatoes since Idaho, and so we wanted a robot that would work in a greenhouse that could harvest potatoes, and because potatoes are usually grown in rows, and that's a lot easier to do in a greenhouse. And we wanted it to be able to progress down each row and harvest each row of potatoes. And additionally, we decided to have the robot on rails, since you could mount rails inside a greenhouse above each row of plants.
Hello, my name is Luis Cardenas, and first I want to talk about what was our initial final goal. Initially, we thought about having a robot to be mounted on a rail, so it would be a certain amount of feet over the ground, so it could easily move and don't have any problem with the dirt or anything that's in the floor. So here there is a little animation of what it's supposed to do. It would just harvest row by row, as you can see in this animation. And once it's done doing it, it would stop at the end of the rail. In order to do this is more like the horizontal view instead of the view at the top. We would need to have some sort of fork that could harvest the potatoes that is on the ground. And this fork should be able to move down and then able to move forward to harvest the potato, lift it, and drop the potato behind, and then keep going to the next row. Due to the fact that we didn't have enough budget to build the rail, and also because of matters of time, we decided to reduce the scope of our project and just make a robot to be moving on above on the ground. As in this animation, you can see it would just move, put the fork down, harvest the potato, and then move to the next row.
All right. My name is Juan Chen. I'm going to present, guys, about the hardware we use for this robot. So we decided to use Arduino Uno since it has more libraries to operate stepper motors, and also it's fast enough for what we wanted and has enough pins and It actually has a cool feature. It has a V-in pin, which we use to power our Arduino Uno instead of using the computer. In that case, our robot will be working itself without depending on a computer. And yeah. And to power our system, we decided to use a voltage regulator instead of using batteries. Since we didn't have enough budget, we decided to use a power supply voltage regulator. And also, since this robot is planned to be using greenhouses, they have the infrastructure already, so there is no need to use batteries. And here are some of the so for example, we wanted this to step down the voltage and then convert it to DC. So going from 120 volts AC to 20 to 24 volts DC. And this voltage regulator has a 25 amp maximum output current and provides 600 watts of power. We also use this DC voltage regulator since our Arduino Uno board needs a 5 volts input, and we use this to step down the voltage a little bit more to 5 volts. And it's also capable of handle a maximum output current of 3 amps and a maximum output of 40 volts on DC. For our motors, we decided to use this stepper motor NEMA 17. It's rated or recommended to be powered between 20 to 24 volts, and the current rate is 2 amps per phase. So we decided to use this driver. It's called the DRV8825, and the chip is designed by TI, but later we will explain what problems we face, but we didn't buy the original ones, and this one only outputs a maximum current of 1.5 amps. So, and it can also output a voltage of 8.2 volts to 45 volts. And it has also, it's able to do microstepping, which is really cool. Since if you microstep, you can slower your motors, and also it's able to use more current. And so yeah, this is what we use for motors and motor drivers.
All right. As for the other accessories mounted to the robot, we needed, of course, harvesting equipment, and we decided to go with a simple raked fork that would just be dragged through the dirt and would be pulled up. So it would be mounted on a set of brackets, and those brackets would be tied to motors. And you can see the top right picture. We have the motor connected to a pulley system, and that actuates the rake. And then we also needed some edge stop sensors so the robot could detect when it reached the end of the rails. So we used these simple limit switches, and we mounted them using custom brackets we designed. and they were pretty electrically. They were pretty ideal for the job since they had a lot of options for how to arrange them, and they were also decently durable. As for the frame itself, we decided to go with some basic 2020 aluminum extrusion. So these are basic T-slot aluminum beams that have 20 by 20 millimeter sides. We chose this because they're relatively inexpensive, but they're also very flexible. You can turn them into basically any shape you want, and they're also very strong. So using the mounting brackets, we could simply cut these beams to length and then bolt them together to create a very sturdy frame that's pretty lightweight for the strength you get out of it. So this is the design for our frame. It's a basic square. That middle section, the large middle section, is where the rakes will sit. They sit in between there, and that gives them access to the ground. And then the front of the robot has additional support with the additional beams across it, and that is where we mount the power supply as well as the other electronics in their own little box. So as for the other components, some of the components that we were not able to find suitable parts online that were reasonably priced, so we decided to pre-print our own. So we 3D printed the wheels, and these wheels are designed for the rail system in mind. Obviously, we don't have the rail system for demonstration reasons, but the design of the robot is intended to travel on a set of rails on either side of the plot and farm plot. And these wheels facilitate that. They have an indentation. They're concave in the middle, and that allows them to sit through on a round rail. Additionally, we printed on the left, we 3D printed a set of bearing holders for the front wheels, or rather the back wheels. The back wheels weren't powered directly by the motors, so we needed some way to attach them to the robot. So we used a set of axles, and those axles sat in these 3D printed bearing housings. So they would hold a bearing, and we'd slide the axle through the bearing. And then on the right, you can see the model we used for the brackets that mounted our limit switches. They were just simple brackets that were laser cut out of acrylic, and that's how we mounted our switches. And then this is everything put together. You can see the wheels, the front wheels with the motors attached to them, as well as the power supply and the box with all of our electronics. And then you have that middle section with the rake, and the rake is mounted in a similar method to how the back wheels are mounted. How there's an axle going through, and there's a little bracket that holds bearings that hold the axles in place. The rake axle was held in place by purchased brackets. We didn't have to make those custom like the wheels.
So here is a hardware block diagram. This is how everything is connected together. As you can see, the power supply receive the power from AC 120 volts outlet, the normal outlet that you can find any place. And the power supply powers the voltage regulator, which decreases the voltage from the 24 volts to 5 volts that the Arduino Uno requires to work. And at the same time, the power supply also provided 24 volts for the step-in motors. But these 24 volts go through the motor driver first before going to the step-in motor. And also we have the signal coming from the Arduino towards the motor drivers. And here we can see how we have the lines in yellow that are a little bit thicker. It means that they carry several wires, while the ones that are a little bit thinner, it carries less wires. So the lines that are coming from the Arduino Uno to a motor driver, they are holding several wires that connect from the Arduino Uno to control the motor drivers. And then the motor drivers allow a signal of 24 volts towards the step-in motor. And we also have the start button that we are connecting this button to 3.3 volts of the Arduino Uno. And we are using two limit switches that are receiving ground from it. And this is how we arrange our electronics also in our robot. So now here we have the actual electrical schematic. As we can see, it's very similar to the block diagram, but we can show here the actual electrical connection in case someone is interested, they'll replicate our model that we use. And even if they are interested in manufacture their own PCB, this is how they could like arrange the electronics.
All right. As for the program, the program we were running is a simple harvesting. The simple harvesting routine we programmed is one that didn't really have any parallel processes going on. It was all sequential. So as a result, we decided to use a basic control loop rather than an operating system. And so this control loop would go through several states, and each state would be controlled by either an interrupt or a condition based on the context of that state. So at the start, they would initialize all its variables and create the motor objects that the motor driver library uses. And then we'd start with a basic idle state, which once it received a signal from a push button that we have, that would signal it to start, which would transition to its state. And then the initial state is a calibration state where it reverses until it reaches the very back of the plot, and the back limit switch is hit. And when that happens, then the robot knows that it's at the very, very start of the plot, and so that it resets all of its tracking variables, so its position and its cycle count. It resets all those to 0, and then it moves on to the running state, which is the start of the harvesting routine. And from there, it goes back and forth between the running and harvest states, where it will move forward a little bit. That's the running state, and then it'll move the forks. That's the harvest state, and then so that will loop continuously until it reaches the end. If the front bumper has an interrupt that will stop the drivers from actually proceeding, and when that happens, then it will enter a halt state. And this halt state can be entered from several locations, and it can either happen when the front bumper is hit, and which either indicates that it's reached the end or that it's hit an obstacle. In that case, if it's just a front bumper interrupt, then it'll go to the wait state. But if it was an error in the code, or something happened where it got stuck in a loop, and the cycle count passed we use a cycle count so that all the loops we use to step the motors don't get stuck. So if a motor gets stuck and keeps going, then eventually it will hit a limit where the number of cycles passes a set number, and then if that happens without it transitioning to another state, then we know that something got stuck, and that also causes it to go in the halt state. And in the halt state, if that wasn't the cause, if it was a simple error and it got stuck, then we also have a resume state where we can push the start button again and it will return to its last position. All right, and then here's the basic code. So we have a header file that contains the variable that contains our pin numbers as well as some parameters for the how many steps we are separating the motors by, as well as convenient names for the states. And if we go to our code, we start with declaring all our variables and initializing our motor objects. The library we use has a special class that handles the motors, and so we have to initialize each motor as an object. So that happens right there. And then if we go scroll down a little bit more, we can see we're setting up the motor parameters with their max speed and acceleration. This driver is convenient in which it has a routine for accelerating the motor smoothly instead of abruptly, which makes it a lot less harsh and it makes the job of the motor a lot easier. And then we go down even further to the loop. And this is our basic control loop. So we'll go through each. So we use the state variable to determine what the robot should be doing. And in each case, we will run an additional, in each case, we run a loop that will do different things depending on the case. So in the basic harvest routine, for example, right here, we see in the harvest and running routines, we see there's a loop that will run the drive motors. There's a function below that just simply steps each motor once. We have to step through the motors manually in a loop since we are running more than one motor at the same time. In this library, most of the functions that step motors automatically are blocking, so we could only run one motor at a time. In this case, so we have to manually loop through and step the motors manually so that we can run two at the same time. And if we scroll down to the very bottom, we can see the functions some of our declared functions, and this handles things like telling the motor driver its destination, which in the library it goes by number of steps. So if you give the motor object a location that's a certain number of steps away, then the library will calculate what commands it needs to send to the driver in order to turn the motor to reach that point. And so we separated most of the things in the loop above into these individual functions just to clean things up. So for example, and then we also have our two interrupts right there. So you can see the void, the back switch handler handles the switching over to the running mode. So if the robot is in initialization mode, which means that it's currently in the process of reversing, and then we know that when this interrupt triggers that it's been reversing and that we know we're now at the very back of the thing. So we set the motor's positions to 0, and then we set our own variables to 0, and then we set the robot state to running, telling it that it can now progress forward. So that's the basic overview of the code. And now we have a video of, we recorded an earlier video of it actually being demonstrated. All right. My name is Brandon, and I'm going to be showing you around the robot that we built for embedded systems. And here it is right here. Now this is our harvesting robot. It was designed to be used in a greenhouse, so it's a little on the smaller side. So if you compare normal harvesting machines like a combine harvester, you'd expect them to be massive. This one's a little on the smaller side, also because it's kind of a proof of concept as well, because harvesting machines tend to be a little bit bigger than they need to. So I'll walk you through some of the components. So this silver box right here, this is our power supply. We decided to use a AC power supply to power the robot, as it was both cheaper and more reliable and simpler compared to a battery system, as well as since we know this is going to be used in a greenhouse, it's going to have access to it's going to have easy access to line power, so by using an AC power. And right now we just have it connected to an extension cord, but you can imagine a system where it will draw power from the rails it's riding on. So that leads into our little control box. If I pull the lid off the control box, you can see the circuitry we're using to control it. So here's the Arduino. That's running the program, and it's connected to, and it's running control signals into these 4 chips, and these are our motor drivers. And they look different, but they're the same type, even though the boards are different colors. And those are in charge of taking the control signal from the Arduino and outputting the voltage to drive the motors, because the motors take a voltage that the Arduino can't handle, so the motor drivers are in charge of handling that. They get their power from this distribution board, which splits the incoming one of the 3 incoming channels from the power supply into separate wires that go to each of the motor drivers, and we separate and then the other channel is going into this voltage controller, this voltage regulator. This voltage regulator is set to 5 volts, and that's being pumped directly into the Arduino, which allows the Arduino to operate on its own without any external connection to a laptop or something like that. And we can follow the motor cables. The motor cables come out, and they get split up to each of the 4 motors. We have 4 motors on this machine. They're all stepper motors, and we went with stepper motors because they are more precise and easy to control, and they mount a lot easier they have easier mounting options. And then here are our limit switches. We have one in the front and one in the back, and since the motors don't have encoders, so that's how we tell the robot to when it's reached the end of the rail, or when it's reached the boundaries, and so it doesn't run off the course. All right. So here's the robot as it's going through its harvesting technique. It's programmed to move forward a set distance for each row of crops, and then the rakes are supposed to flip upward, and any like potatoes or beets or any underground plants would get scooped up and set off, and by flipping it over, it would get laid out on the dirt. Now, unfortunately, with this machine in question, this showcases one of the main flaws with this implementation right now, which is that the motors lack a lot of power, and you can probably hear the motors as they're trying to actuate. The drive motors are moving forward, and the rake motors are trying their hardest to lift the rake up and then set it back down again. But unfortunately, the rake is a little too it's a little too heavy for them, and they don't have enough torque to actually do the movement. And I guess that's the downside with stepper motors, is that while we gain a lot with precision, we lose a lot in terms of power for the given amount of current.
Okay, now we are going to talk about a little bit of the struggles we have with our project. First, the stepper motor we decided to use didn't provide enough torque to actually move the car and lift the forks. So that was one of the initial problems. The other problem we have was that the internal resistance of the stepper motor was out of specs. So it was supposed to be 1.6 ohms, but we measured with the DMM and it was actually 2.1, which means that the stepper motor was actually trying to draw more current out of the motor driver, which was overheating the motor driver. And as you can see here, we have some pictures of some motor drivers that we burned because of this issue. We burned around 3 or 4 of them, and some of them never work at all. Another struggle we had was due to the limited budget that we have, we didn't have the chance to improve our project and upgrade for the parts that we needed. So we realized that we needed to change our motor drive for one that could provide more current to the stepper motor, and the stepper motor that could have more torque. So because of the budget, we were able to buy more to upgrade the parts. And some of the components that we had bought before were low quality components. So we were going to talk in the future a little bit on the improvements, things we suggest. And some of them is buying better quality components. Another struggle we had was to balance the time between the hardware and software. As we invested more time trying to debug things in the hardware, we didn't have enough time to actually debug the software. And that was an issue of how to organize our time to work in both things at the same time. And another thing is we didn't have enough time also to apply the improvements and order new parts to replace for the parts that weren't working as we expected. As part of our debugging methods, we use a logic analyzer to read the stepping signal coming out of the microcontroller. And we also use it to check it was providing like a correct square wave to the motor drivers, the microcontroller, and also we did to check the direction of the signal, the direction signal from the microcontroller to the stepper motor to control the direction of to the motor drive to control the direction stepper motor. We also use a DMM to measure the input voltage that were fed to even the motor drivers and also to the microcontroller. We also use the DMM to measure the current that the motor drive was feeding to the stepper motor to see it was providing enough current to drive the motors. We also use it to measure the internal resistance of the motors. That's how we realize that the internal resistance of the motors was out of spec. Also, we use a function generator to create a step signal that we apply to the motor drivers. And we use the oscilloscope to read the output signal coming out of the motor driver to see if it was providing the correct signal that needs to be feed. It needs to be feed to the stepper motor. We also did an integrity test of the motor drivers. Once we made one of the motor driver work in the way that we wanted, with the arrangement of the electronics and all set up correctly, we exchange the different motor drivers to see which one were working well, which one weren't working at all, and so we can just use the ones that were working correctly. And some of the outcomes that we have through this project, first was we were able to identify the reasons why the drivers couldn't drive the motors correctly. So we needed, as mentioned before, we needed to do a lot of testing, and we spent a lot of hours until we finally realized that the problems was some of our components were out of spec, and they didn't providing the torque or the current that they said that they were providing their specification and then data sheet. And also, one of the outcomes was having like a robot, harvesting robot built. We designed this harvesting robot. The idea was original. We designed the frame, we custom parts, we did the electronic selection, and we mount the parts, and we also mount the power supply, and we made all the electronic connection and program the robot. We also were able to have a robot that was able to move back and forth over the floor, and also it has a power autonomy since the microcontroller was receiving the power directly from the power supply and didn't need to be connected to a laptop, computer, a PC to receive the power.
As conclusion, this point of the presentation, you have learned about the components we use for a project and also explained the struggles that we face and the outcomes that we achieve. However, there is always room to improvement. And as we explained, the motor drivers that we chose didn't deliver enough current to power our motors. And also the motors that we chose didn't have enough torque to lift our fork. So to solve this problem, we can use the DM542T motor driver, which is here in the top right of the screen. It provides more current, up to 4.2 amps per phase, and compared to the one that we use, only deliver 1.5 amps. And additionally, we can use the high torque NEMA 23 step motor, and this one is way bigger, but also it holds a torque of 3.0, if I'm not mistaken, it's Newton meters. And instead of the one that we picked, only 59 Newton centimeters, which is a big difference. And further, we can also replace our fork with a sturdier one, since we are planning this on using to lift potatoes and bury on the ground. It needs to be strong enough. And replace also the AC power core with a more sophisticated power supply from the rails. And the things that we learned, well, as Luis was explaining, we had a lot of time troubleshooting hardware components. So we gained more experience how to use multimeters, oscilloscopes, function generators, and also we learned how motor drivers work and how the step motors are connected to motor drivers and the right pin configuration. And also this project was time consuming, so we learned how to plan better and how to communicate and delegate responsibilities. And we also learn how to use power supplies and voltage regulators to power up our entire system. And so these are the things that we learned, and thank you guys for watching this whole video.